Welcome to The Explainer. Today, we are tearing into the intense chemistry and physics behind thermobaric and enhanced blast explosives. We're looking at a fascinating, incredibly detailed study from the Central European Journal of Energetic Materials that breaks down exactly what happens when these devastating composite materials detonate inside a confined space. It is a literal masterclass in manipulating materials at the microscopic level to engineer maximum macroscopic destruction.
Here is our roadmap for today. We're going to quickly cover the anatomy of a blast, how to brew the perfect boom, what happens inside the explosion chamber, a really clever air versus argon test, and finally, reading the blast residues. Let's get right into it. Part 1, Anatomy of a Blast, TBX versus EBX. Okay, so before we get to the really crazy science, we need to nail down what actually happens when these things go off and how they're different from standard explosives, like say TNT. The big takeaway here, both thermobaric explosives, or TBXs, and enhanced blast explosives, or EBXs, rely heavily on metallic fuel, usually aluminum, and they use this aluminum to create a massive secondary spike in energy after the initial blast. You see, a conventional explosive just releases its energy in one quick, violent burst. But these fuel-enriched formulations, they hit you with a primary shockwave and then follow it up with an intense, lingering fireball. They are designed to exploit their environment, especially confined spaces, to maximize thermal damage and overpressure. But they go about it in slightly different ways.
And that brings us to the core difference. It's basically about how they breathe. Enhanced blast explosives essentially suffocate in their own afterburning. They operate completely anaerobically, meaning they use the scorching hot detonation products themselves to react with the aluminum fuel and push that shockwave even harder. On the flip side, thermobaric explosives are aerobic. They breathe in the surrounding air. They literally suck up ambient oxygen to cook up this massive fiery pressure spike. Now, when you set these off in a confined space, the shockwave reflections and all that turbulent mixing kind of blur the lines between the two, which results in just an unbelievable amount of destructive power.
Moving on to Part 2, Brewing the Perfect Boom with the Wet Slurry Method.
So how do researchers actually engineer these microscopic granules to squeeze out every ounce of blast energy? It is an incredibly precise science. They use something called the wet slurry method. Think of it kind of like a highly dangerous microscopic baking recipe. We're mixing explosive ingredients into this liquid dough. First, they dissolve a Vitin binder. Then, they mix in RDX, that's the high explosive, along with ammonium perchlorate as the oxidizer, and of course our aluminum powder for fuel. By slowly adding an anti-solvent, they form these tiny liquid droplets. Finally, they carefully evaporate the fluids to lock everything down into perfect multi-component spherical granules, each one just about 1 to 1.5 millimeters across.
Now, check out the difference between these two granule designs. It's a really stark contrast. We have configuration A, which is a tightly packed homogeneous granule, where everything is perfectly mixed together. Then we have configuration B, this kind of lumpy core shell setup, where an explosive RDX shell wraps around an aluminum and oxidizer core. Now, you'd probably think the highly specialized core shell design would be the winner, right? Well, surprisingly, it completely underperformed. The data actually showed that the outer explosive shell just couldn't transfer enough heat inward to properly ignite that aluminum core. It turns out the totally homogeneous mix with all those ingredients in intimate contact was way more efficient.
All right, Part 3, Inside the Explosion Chamber, Testing the Blast. So we've baked our microscopic explosive granules, and now it's time to actually test them out. To do this, the researchers built a heavy-duty 150-liter steel tank. They suspended these incredibly precise 43-gram charges right dead in the center of the chamber, sealed the whole thing up, and wired the walls with ultra-sensitive piezoelectric pressure gauges. This rig let them safely detonate the charges and measure what's called the quasi-static pressure, or QSP. Basically, they're capturing the exact force generated by both the blast wave and that resulting fireball inside a perfectly confined space.
And when we break down the timeline, you can see this pressure building millisecond by millisecond. It's wild. At exactly 0 milliseconds, the charge detonates. Less than 10 milliseconds later, that initial shockwave is already violently ricocheting off the steel walls. All that reverberation whips up this massive, turbulent vortex of superheated gases, which physically forces the aluminum particles to ignite in that secondary reaction, peaking right around 20 milliseconds. By about 40 milliseconds, the overpressure finally starts to stabilize. What they discovered was that these aluminized charges produced maximum overpressures that were significantly higher than just pure TNT. The aluminum was absolutely pumping massive amounts of extra heat and pressure into the blast. Which leads us to Part 4, the air versus argon test, aerobic versus anaerobic. So they knew the aluminum was adding pressure, but the researchers needed to know exactly how it was burning. Was it using the oxygen in the chamber air, or just the gases from the explosion itself? To figure this out, they designed a brilliant test. They flushed the whole chamber and replaced the oxygen-rich air with inert argon gas, creating a completely anaerobic environment. And the results are pretty amazing. The first data point shows the blast in normal air, hitting roughly 0.79 megapascals. The second data point is the argon test, which drops to 0.66 megapascals. This proves for sure that aerobic burning using surrounding oxygen creates the biggest pressure spike. But look at the baseline. If the aluminum hadn't reacted at all, the pressure would only be 0.47 megapascals. Because that argon test hit 0.66, it definitively proves that the aluminum is still fiercely reacting with the raw detonation products, even when it is totally starved of outside oxygen.
And this data gives away a vital secret about how the actual physical geometry of the charge dictates the whole blast. When they compared standard, homogeneous cylinders to charges that had an explosive core wrapped in a thick outer layer of aluminum, they found something fascinating. Those tightly packed homogeneous charges did amazingly well in the oxygen-starved argon environment. They acted like true enhanced blast explosives that don't even need outside air because the ingredients are perfectly mixed to just react with their own hot gases. On the flip side, the layered charges completely thrived in the air blasts. They actually rely on the initial explosion violently throwing that outer layer of aluminum outward into the surrounding oxygen to work as a devastating thermobaric weapon.
And finally, Part 5, Reading the Blast Residues, Forensic Analysis.
To wrap up this investigation, we really have to put on our forensic hats. After the blasts, the researchers opened up the chamber, swept up the leftover ash, and threw it under a scanning electron microscope. And the visual evidence they got is absolutely staggering. Looking at the air blast residue, the oxygen-fed fireball burned so incredibly hot, we're talking over 2,800 degrees Kelvin, that it completely surpassed the melting point of aluminum. The metal literally melted into perfect submicron liquid spheres, oxidizing beautifully. But from the suffocated argon blast, the chamber barely reached the melting point. It just left behind these jagged, unmelted chunks of aluminum caked in carbon soot. It barely reacted at all, simply because it couldn't fully melt.
There's a quote from the researchers that perfectly nails this forensic thermal analysis. They state that the aluminum must be in the form of submicron liquid droplets to react and create aluminum oxide during the explosion. This proves that just having a massive shockwave shatter the granules isn't enough. If you want to unleash that devastating secondary energy, the initial blast has to generate enough shear heat to physically melt the aluminum into liquid droplets. Only then can it fully oxidize and drop its full payload.
As we wrap up this explainer, I really want you to consider the sheer scale of what we've unpacked today. Think about how a fraction of a millimeter difference in how we structure a single composite granule, or just whether a charge is perfectly mixed versus layered, can completely rewrite the destructive thermal reality of a macroscopic blast. It's a chilling, but honestly awe-inspiring reminder of how mastering things at the absolute microscopic level fundamentally dictates the physics of the world around us. So what other microscopic tweaks could completely redefine the limits of materials chemistry? Thanks for joining me on this deep dive.